Hi everyone, my name is Tue Ly, and call me Ly, and I'm currently at Google, and I'm one of the libc maintainer, and I'm focusing on the math functions. So today I'm going to give an update about our current status and the future directions that we are heading to. So for a lot of you who are new to this, so what is LLVM libc? So we are a greenfield implementations of the C standard library under LLVM umbrella. And we are focusing on the C23 standard, the latest one, and we also fill in with the POSIX and other things that the users need. And the implementation language is mostly C++, and we bring in some little inline assembly. And so what is our goal? Our goal is to implement complete C23 standards. There will be a link if you are looking into. And a bigger goal is we want to have a one libc for everyone, whether it's any of the operating systems that you care about, or some of the modern CPUs that are people interested in, or embedded system use case. And we also worked on the GPUs. I wish that someone from Intel can give us some of the Intel GPUs, then we can add it. All right, and here's the link to the homepage. And so what is about LLVM libc math functions, or the libm? So we're implementing all the C23 math function, focusing on the highest priority is accuracy. And of course, for it to be useful everywhere, we need performance, also portability and configurability, because we know that there cannot be any one-size-fits-all for everyone. And the standard right now that we're focusing on is on the binary floating point IEEE 754. And the latest standard is 2019. So this is the homepage status, and I'm going over more details about what we are really focusing on. So about the accuracy, how accurate are we implementing the math functions? And if you heard the hints from the previous talks, so we make it as accurate as possible. And the ultimate goal is to make it correctly routed for all routing modes. So at the moment, we tested on the 4 default routing modes on x86-64. I know that ARM has another routing modes, but we didn't have we didn't have time to edit for that routing mode yet. It's tied away to zeros. And actually, I don't know the macro name for that yet. And right now, we are doing what they call the dynamic routing modes, where the routing mode is specified by the floating point environment. But then, of course, from the dynamics one, you can do the static routing mode simply by enforce the routing mode at the beginning and at the end. So one very big advantage of correct routing math function is that it will imply consistency. And this consistency will be across all the platforms, all the CPUs, all the OS, and anything you can think of, and even the library functions. This will significantly reduce the toll of updatings or integrating the new libc versions or libm versions into your applications. Because and we do see this advantage, or this one play out inside Google when we integrating the new math functions. And the floating point, especially right now, there's a lot of machine learning AIs where they essentially just store all the bits of the floating point results into the database. And with more consistency on the math functions, we will be, hopefully, more confident that the data models will be the same wherever you load, store, load, or compute it on ARM or x86 or GPUs. Okay, and so here's the accuracy report across the libms by the researcher group in INRIA, and this is for LLVM 18, and so far I was the only one that tried to be as accurate as possible. With 19 and 20, we are going to have more, and we are going to steal some of the spotlight at the bottom from glibc and IML. All right, so a lot of people concerned about the performance when we talk about the accuracy. So at what cost are we accept in order to reach that accuracy? Well, turns out not bad at all. So overall, you can so this is the plot about the latency relative to the glibc, the system libc that I have on the machine, and this is on the AMD, some of the AMD server. I believe it's Zen 3, and so this is the lower the better. And as you can see, that some of the functions that we are a little bit slower than glibc, but a lot of them we are actually a lot faster. And this is for the latency, and you have this, on average, if you take the geometric means of all of them, we are about 15 or 16% faster than glibc, or lower latency than glibc. What about the throughput? You have actually similar plots, and it's actually a lot better on the right-hand side. So on average, we are about 25 to 30% faster than higher throughput than glibc. Sorry for the plot that I put it as reciprocal throughput, so that it has the same shape as the latency. So to get the throughput differences, you need to invert them. All right, and this actually helps us to reduce the computational cost a lot thanks to the machine learning and AI, because one of the very hot functions in machine learning and AI is hyperbolic tangent. And we are significantly faster than any of other libraries right now. About portability, most of our functions implementations are in platform agnostic, C++, or you can say that it's on sort of like C style C++. And it can be built on any platform without floating point units, or even without a floating point runtime library support, thanks to the current effort. So we are having all the pieces that we need for a generic soft load library. So we have the integer-based implementation backup for all of the basic floating point operations. And we also have a template big integer class that surprisingly works quite well, even for 10,000s of bits. You might want to optimize for the performance of your target if you need to. But so at the end of the day, all you need to do is just a single integer type that we can spawn up the whole entire floating point environment for you. And all of the platform-dependent annual and floating point exceptions can be omitted within our library with some configs. Well, that needs some work to be done, so that you can build a standalone libm library that doesn't depend anything on libc, and that can be run anywhere. About configurability. So we provide, in our libc, we provide a support for various use cases at build time in your config. So you can create your own set of math functions that you like. There might be some dependency, hopefully that to be resolved. Within just create some of the text file, list the functions, and pass in the path on the cmake command. We also started to provide some of the optimizations options for your math functions, like no accept before routing modes, and small try to optimize for code size. By so far from what I've seen, the one that takes the most of the code size is the lookup tables. And also we can allow you to be a little bit less accurate by skipping the final accurate pass, because that's actually pretty costly. But then we can provide the provable up-bound errors for those implementations. And well, we group them all, we call them list fast math or math fast. Maybe this is the real one that you're looking for, just in case. All right, and anything else, if you have any of the optimization that you need that is not fitting here, please let us know. All right, so what is our current progress toward C23? Well, plus, because there are some extra things in there. I love this one from the reference on the difference with the new things on C23 for the math library. Well, just one line. Anyone from the C standard library? Sorry, from the C standard here, committee here? Do you know how many of the new math functions added in C23 versus the previous one? Or how many in total? Thanks. So we to collect the most. So in C23, recently we added new two floating point support. The half precisions, which is the float 16, and the quad precisions, which is float 128, ish. There are some caveats over there, depends on your platform. And we also add the fixed point, which is a C extension that I did 15, 20 years ago. And recently, we completed all the basic math operations for all flight floating points. And yes, there's a summary for you. It's about 300 something. And here's the detailed list if you're interested in. There are some differences in the number of you, depends on how you count it. For example, I would count the square root as a non-basic operations, even though most of the hardware support it. But for example, the float 128 does not support it in hardware. And this is the link to our current status, if you're interested in. About the higher mass functions or transcendental functions, well, transcendental plus some other one like cube root or hyperbolic, hypot. And currently we have about 1/4 of them, and all of them are correctly routed to all the routing modes that we tested. And there are currently 3 of them that I only implemented the FastPass, which has 1 UOP. So basically, it just you might be different at the last bit. And I plan to fix them before C20 cutoff. So here's the list of them, and we finished most of the C99 float functions. So I think there are 3 missing C99 functions that we needed. The rest of them are C23. And the double precisions focusing on the long double, as Joshua mentioned earlier, is like mapped to 4 types. So we would like to focus on 1 at a time, and then we will fix for the long double later, unless you really need them. And the float 16, even though it's new, it's making a very good progress, and it will catching up with the float and double very soon. And we also started to work on the float 128 higher math functions. So this is the current link to the current status page. All right, so let me go a little bit into detail about the C23 type support for high precisions. So this is the name specified by the C standard. And this is kicked off with the Google Summer of Code project that we're lucky to have this summer. And the end result, we have a blog post by Nicholas. And he's going to talk more about that tomorrow. So if you're interested, please attend. And here's the link. All right. It has a very great performance potential with the future hardware when we have support. And we do see that with some of the newer phone that we try on. And I think it's going to be very good use for other small platforms. But, well, there's no fun if we don't have anything broken. Well, for example, we have like which cast, we run into like which cast function, the built-ins that work on all the platforms that we care about. And what about Clang versus GCC generated code, or the ABI, and compiler RT and GCC. So thanks, Nicholas, he ran into these very detailed, and he posted these. So I'll keep the link in here, but I won't show it to you, because so that if you're not following the link, you can go to Nicholas' talk tomorrow to see those. All right, about class precisions. The C23 type specified as float 128. In real life, it's a little more complicated than that, but the float 128 is a very good replacement for if you want the platform consistency to run across the platform. Because in case you don't know, and in case Joshua didn't mention it explicitly, long double is 80-bit floating points on x86 Linux. It is literally just double precision on Windows and macOS, and I think there might be more. It is 128-bit quad precisions on ARM, RISC-V, and Android. And this one we just learned about very recently. It is double on PowerPC. And I really don't know how they implement that in hardware or experience. So, well, just like long double has some weird things with their type, quad precision also have similar things. Which one are we going to use? Can you guess? I actually don't know either. Yes. Because for C, you don't have much problem with the ABI. But we are implementing in C++, and most likely this is going to be supported in C++. And it's going to hit into the ABI issues or the name mangling issues with these 3 mixings around. And I hope the committee somewhere here to help us to figure it out. Okay, C or C++, Clang or GCC, and this is a quick investigation that we have. All right, and the new one that from the C support is the fixed point. So this is specified in 2008 as extension for embedded processors. And we're implementing, right now, Clang and LLVM libc is the only open source options you have for fixed point out of the box. This does provide significant speed up and cost size reductions when it's applicable. So we used them, one of my colleagues here, and we worked together and put them to replace soft load on PixelBed. And the current support, we have just a few functions that needed by that project. But if you are interested in provide your special fixed point functions, please come to talk to us. So for the near future, we'd like to finish all the C23 math functions. And this is sort of orders. And also fixed point, we started the complex support very recently. And we want to expand to make sure that all the other platforms has the same priority as what we have for x86-64 right now. I think currently the blocking one is just we need more people, we need more help, and we need more bots, actually. Then also on the OS side. So a little further one, this is a continuous work that we'd like to optimize for performance and cost side for various targets. And I really want to start the vector math library, libmvec, hopefully sometime soon. And Dexter was floating point support, because just for completeness. And also the C++ special math functions is in our list that we are looking into. Next. Also, with the correct routing implementations, then we can support the C+26 ConExpert math functions. And this is the collaborations hand in hand. Please come to my colleagues' talk tomorrow about this collaboration between libc and libc++. And so maybe we can really replace, provide one single implementation for all the runtimes for the math functions to be used in compilarity, built-in AP float, and other runtime libraries. So maybe triple hands. Okay. Any more floating point types like B416? Or we can really make Intel 80-bit floating points to be run everywhere. If you're interested in, please come to us. Or float 256 for shadowing quad precisions if we need to. Special thanks to all the LLVM libc and libm contributors, and the Google Summer of Code for providing excellent support for quad precisions. And the core map project is for us to have the inspirations and collaborations closely. The libm project, and to all of you, thanks for listening to me. For almost. Okay.
Okay, thanks, Tue. Again, we have a mic here. If people want to line up for questions, or if there are questions from this side, I can run a mic over here. Yeah, go ahead, James.
How do you support the new C23F of round stuff in the libc library? The one that lets you do static rounding mode for each of the standard math library functions.
Yes, we can support that, but we will need some way in order to make sure that the routing environment is fixed. And I guess that is the easiest way to add current support for the CR, the correctly routed math function in C23. But there might be some performance penalties. And if the performance becomes prohibitive, then maybe we can try to rederive different algorithms for those routing modes. Yeah.
Are there any configuration knobs to reduce the accuracy and increase the performance of this library? Because sometimes we just don't need the correctly rounded result for these functions.
Yes. So for single, so we do want to add extra options. It becomes like the maintenance cost, right? So if someone really need those, they can create issues, and we might look into, because those have to be like based on the function basis. Mm-hmm. And most of our implementation for single precisions, it's just a single pass, and there's no accuracy pass at all. So unless you change things inside the implementation, it's going to be a little tricky to control the errors. But for the double precisions, we do have to run on the fast pass and the slow pass. And right now, the fast pass, we do have the static, or we do have the formal proof of the error bound. And that is the current easiest options that we provide right now. It's just use the fast pass and forget about the accurate pass. But if you really need a much lower precisions, then if there's a need for that, we can specialize for it. Yeah.
And another question. For instance, I want to run this library on some specific hardware, and my hardware has a hardware instruction that implements some function. Can I specify target-dependent implementation for a function in your library?
Yes, you can. Yeah, there are ways for you to add extra. But I guess the best way is to add them into the built-ins, if possible, the compiler built-in, so that we can just rely on the compiler built-ins instead of like have to do the inline assembly.
No, I mean, assuming we already have intrinsic and built-in function.
Mm-hmm. Yeah, then definitely you can.
Thank you.
As someone who has no idea about the implementation of this sort of stuff, I'm just curious as to why you can't like templatize the implementation of like a math function for all the different bit widths.
So, in general, for some of the functions, especially the transcendental functions, the fast way to do it is to do the polynomial approximations. And to control that errors, theoretically, we can sort of templatize them, but it's extremely hard, and it will not satisfy the performance for different types. And lucky for us, right now, there are not that many types, but if there are like 10 or 20 types, maybe we'll sacrifice the performance a little bit for each of the types and then just templatize them all. Yeah, thanks.
Hey, so in your list of the build options where you can build the libc with different configurations and ignoring different things,
yeah.
I didn't notice one for, do you have an option to build ignoring nans and infinities to get rid of the special checks?
Yes, I just think about that when in your talks, and definitely you can create an issues, and then we will address that.
And when you build with those different options, is there a way to get it to like build that into the function names so that potentially I could link against multiple implementations and choose based on?
So the capability for updating our build system or our macros to alias with the different names is requested, and we are going to address that soon, because sometimes you want a single functions but then have multiple names. For example, if you want to pack it into, for example, the long double one in ARM, you don't want to have two copies of long doubles and float 128. You want they are alias to the same functions, and yes, we are going to address that.
Okay, thanks.
Thanks.
Hi. For the vector library,
Yes.
do you expect that the results will be the same as the scalar library? Do you have an opinion about that?
So our aim, the vector library is going to be somewhat similar to what we are doing with the GPUs, that if you are requesting the most accurate one, you don't pass in the fast pass or anything, then most likely we will run the fast pass on the vector versions, and then we will do a quick check. There's a test to see whether the result is correctly routed or not. And if it's not, then we will run the scalar for those that fail. Mm-hmm. And I think that's going to be the approach that we are going for the libm Dev. And so currently the failure rate for the accurate pass, we aim for it is about at least the accurate pass should be like at least 99.99%, something like that. So that is going to be very rare for you to hit the slow pass. Okay. But yes, you can chop that up.
Okay, great.
Yeah.
And what's your plan for FP1?
So I saw that
One
your
very quick
choice was C++. Do you expect that to be a hurdle in bootstrapping embedded targets?
Bootstrapping on embedded, our embedded contributors are helping us to. So bootstrapping on embedded. So I think there's a current effort to make the libc first and things work on embedded system. So I expect that we should be able to help somehow.
Okay, I guess like the question is that you will require a cross-compiler, C++
yes.
compiler, as opposed to starting with a C compiler.
Yes. Yeah. Thanks.
Okay, thank you very much. Thanks.
Thanks.